So today we're going to talk about building intelligent video search pipelines with multimodal AI. So earlier at the keynote, CJ introduced Voyage Multimodal 3.5, which is MongoDB and Voyage AI's latest and greatest multimodal embedding model. First, we're going to take a look at some use cases for this multimodal embedding model and how we can use that to design systems that helps us retrieve videos and images at scale. And we'll see how to leverage MongoDB's Atlas technology alongside that as well. Next, we'll take a look at the capabilities of Voyage Multimodal 3.5, the architecture, some of the benchmark results. And finally, we'll cover video processing strategies and how to make the most out of this new model. So as a quick show of hands, who here is familiar with the concept of embeddings? Okay, so as a quick overview, we have embeddings, which are vectors that represent the semantic meaning of data. This data could be something like text, images, video, etc. And inherently, this kind of data is hard for us to search semantically. So what we want to do is transform this into something called an embedding. Now, an embedding is just a vector of numbers, and what we can do with this embedding is we can place them in a geometric space with the intuition that semantically similar data are going to be geometrically closer. The machine learning model that helps us do this is called an embedding model, which is what we build at Voyage. And once we have them in our vector database, when we want to do a semantic search, we just query the vector database and get the closest results, and that's going to give us the semantically closest search results. So now that we know all of this, how do we actually put this into action? These are some sample strategies for building systems with multimodal embedding models. The first use case is called text-to-video retrieval. So it's just as the name says, for example, if you have a query like a person cooking outdoors over a campfire, what you want to do is retrieve videos that pertain to that search. Now, with traditional search, you might need something like metadata associated with the video, like captions or tags to inform your search results. But the beauty with embeddings and semantic search is that we're using the content that's actually present within the frames to do this search. So even if you have missing metadata or videos with no metadata or cases where the search term is not something that's descriptive but a little more abstract, we're able to get very strong retrieval results using this kind of technology. Now, the architecture for this is rather simple. You have your library of videos. You would process them with a multimodal embedding model, such as Voyage Multimodal 3.5. All of the embeddings would go into a vector database, such as the one built into MongoDB's Atlas. And then at query time, your user with the text query, you put the text query into the same multimodal embedding model, such as Voyage Multimodal 3.5, and you use that to query the vector index that you previously built within your vector DB. So again, the key point here is that we can match on more abstract characteristics in the text and not simply just metadata. Now, another pattern we have is something called video-to-video retrieval. So this is very similar to our previous use case, but instead of having a text query, maybe we want to use actual visual content as the search query. Now, because, again, our embeddings are capturing the semantic content rather than just comparing like pixel-to-pixel similarity like you would do in a more traditional search, we're able to match on traits like motion or intent that are present within the video clips and not just the actual frame similarities. This enables us to have some pretty robust use cases, such as in content moderation or even media analytics, anything that really requires a strong abstract understanding of the video content. When we build real-world systems with these embedding models, typically we augment them for better functionality. These are two sample patterns that are often used in production. The first is something called hybrid retrieval. So with Traditional search, the benefit is you get precise, focused results with metadata. And with embeddings and semantic search, you're able to search on the semantic content of the videos in a more abstract manner. So combining the two of those together, we get hybrid retrieval, which usually looks something like this. Once we have a user query, we're going to perform a vector search to get a list of retrieved videos. Then we're going to perform filtering on the metadata itself. Now this could be for something like permissions or time range or language, something that's a little bit more well-defined. And after that, we'll use that to refine our final results. Now, the beauty with MongoDB Atlas is that the documents contain both the embeddings and the metadata in the same place. So this kind of functionality is pretty much enabled for you out of the box. The next pattern is multimodal RAG. So RAG is like a question answering system that's usually used to augment the responses of LLMs. Traditionally, LLMs are subject to hallucination and bad results just from their training data. So what we want to do is provide the LLM with relevant context that grounds our answer. If we have a vector search system that's coupled with our question answering LLM, what we can do is use the user query to search for relevant videos that are going to give us the knowledge required to answer the user's question. We feed that as context into the LLM alongside the user's query, and that's going to give us a strong grounded result from our question answer LLM. And this is applicable to things like chatbots, assistants, agentic workflows, et cetera. So are these use cases possible with just any multimodal embedding model? The answer is no, and there are two good reasons why. So not all multimodal embedding models are built equally. In the older generation of models, what we call the clip-style models, typically what happens is that inside the model, there are two separate modules. One is responsible for processing the image content, and we have another that's responsible for processing the text. So these are two disjoint modules within the actual model itself. What happens when you give it an input? If it's an image, it gets routed to the image module. If it's text, it gets routed to the text module. And only at the very end are the embeddings from the modules projected into the same space for alignment. And what happens when we have this kind of architecture is that because the two modules are effectively separate within the model, all of the visual content gets clustered together in the embedding space, and all of the text content gets clustered together in the embedding space. So in this example, where we have a sentence and the visual representation of a sentence, semantically, the intuition should be that these two searches are very close to each other in the semantic space, and their embeddings should be almost at the same point. However, because we have these two disjoint modules within the model, typically what we observe is that these actually end up being very far separated, which gives us suboptimal retrieval performance. So we call this problem the modality gap. Another implication of this kind of architecture is that because we route images to one module and text to another, each embedding can either represent an image or a piece of text, but not both. So if we wanted to have interleaved text and media, such as embedding an image alongside its caption, this is simply not possible with the older generation of model. So with Voyage's previous generation, Voyage Multimodal 3, we introduced the ability to have interleaved sequences of text and image at the same time. So that means you can do an image alongside its caption or a paragraph and have that be semantically represented within the same embedding. And now with Voyage Multimodal 3.5, we're introducing the ability to add video into this mix as well. So now we have the ability to do interleaved sequences of text, images, and video all within the same unified embedding space. And really what allows us to do this is a unified architecture for the model that processes all the visual and text content through the same transformer architecture. So instead of having two distinct modules that are only unified at the very end, Voyage Multimodal series are constructed to be unified from the very beginning. This also allows us to bridge the modality gap and also gives us world-leading benchmark performance, which we'll see a little bit later. So taking a brief look at the architecture, let's assume we have a sample input of text, images, and video. The text is processed as usual. It goes through a tokenizer and becomes text tokens. If we have image or video, so any kind of visual content, the first step that happens is something called patching. So first, we pre-process these pixels into smaller chunks of pixels so that we're able to feed them into the next pre-processing step, which is the vision encoder. Inside the vision encoder, several things are happening. So first, we want to group adjacent patches. This means we're grouping information that's close to each other for better feature retrieval. Then we're using a transformer to actually extract the features from the visual data. In the case of video, there's also a very important step, which is the temporal alignment. This means that if we have time data, which video has a time dimension associated with it, we want all of the temporal relationships between the frames to be retained so that our LLM can understand what's happening in what sequence. So that is also performed by the vision encoder, and at the very end, we do a projection to bring everything into the same space. This generates what we call the vision tokens, which are the image tokens and the video tokens, and all of this is concatenated and then fed to our LM decoder, which actually is trained and learned to generate the embeddings. So all of this allows us to get unified embeddings for text, image, and video within the same embedding space without the issue of the modality gap. And because of this kind of unified processing architecture, we have strong benchmark results, especially in cross-modal and video retrieval tasks. I know it's a little hard to see here, but the graph on the left is visual document retrieval. So this is the task of searching for a visual representation of a document given a text query. On the left, on the y-axis is the benchmark performance, so higher is better in this case. And we can see that Voyage Multimodal 3.5, which is at the very top in dark green, is industry-leading and outperforms the latest models from both Cohere and Amazon in this regard. On the right, we have video retrieval, which is the task of searching for a video clip given a text query. And Voyage Multimodal 3.5, again in the dark green, outperforms the only other commercially available video embedding model, Google's Multimodal Embedding 001, by about 4 to 5%. When it comes to embeddings, typically quality is not the only consideration. And that's because we need to store the embeddings inside a vector DB, and vector DBs are costly. So what we can do is we need to find strategies to reduce the size of the embeddings that we're actually generating and querying against. There are two main ways that we can actually accomplish this. So the first is through dimensionality reduction. So each vector or each embedding has an associated number of terms. The fewer terms we have in the embedding, the less storage it takes up, and the less costly it is for us to store and retrieve these embeddings. The second is called quantization, which is when we transform an embedding into a more space-efficient data type. For example, the default is usually a float, which is 32 bits of data. But if we use an integer or even binary, we can reduce that amount of storage space pretty drastically. And the issue with this is that we want to do all of this kind of reduction without impacting the actual benchmark and retrieval performance of the model itself. So Voyage does this with something called Matryoshka representation learning, the details of which I won't get into here. But essentially, it allows us to preserve the quality even at lower input dimensions and quantizations. Now, how this reflects in the benchmarks is that you can see here on the same task, if we use 256 dimension embeddings instead of the native 2048, so this is an 8x reduction in storage cost, we're still outperforming the latest models and our previous generation Voyage Multimodal 3. And on the video embedding side, even with 256 dimension embeddings, which are significantly smaller than the default or what Google provides out of the box, we're able to achieve better benchmark performance. So to reiterate, Voyage Multimodal 3.5 supports dimension options from 256 all the way up to 2048, and a wide range of quantization options that makes it flexible for any use case that you might have. So now let's dive into the specifics of how to use this model to embed videos. And there's an important thing to keep in consideration here, which is the context length of the model. So every embedding model has an associated context length, which is the maximum length of the example that you can input into the model. For videos specifically, this depends on three things: the width, the height, and the number of frames in the video. For Voyage Multimodal 3.5, our context length is set at 32,000 tokens. And for example, if we have a video that's 640 by 480 pixels, so 480p resolution, and it's playing at 3 seconds, 24 frames per second, that's going to give us around 20,000 tokens, which fits comfortably within our context length of 32,000. Sorry, is there a way to play this? Sure. Yeah. Okay. Okay, great. So here we have a sample video, which is 480p, 24 frames, and it lasts around 30 seconds. As you can see, this is a relatively large amount of visual content. So in a second, what we'll do is we'll try to embed this video using the Voyage Python SDK, and we'll see what happens. So first, we load the video. Note that we're setting the optimized parameter to false here. And as a result, our generated embedding, it will give us an error because it's exceeding the context length of the model. And if we look at the estimated number of tokens, it tells us that this video is around 263K tokens, which is significantly greater than what the model can handle. So this tells us that with larger video examples, especially high resolution videos or videos that are several minutes, they're going to struggle to fit into the context window without any kind of intervention. So that means we need a strategy to make these videos fit within our context length so we can generate embeddings for them. What Voyage gives you the flexibility to do is that we'll process these videos as is if you choose to do so. So if you're a pro, you're able to reduce the dimension or the frame rate in whatever way that you might want to. However, if you're just getting started, we do have a default strategy that's enabled in the Voyage AI Python library that makes this easy for you. It's called fixed downsampling, and what we're going to do is extract every nth frame spaced equally such that the final video fits within the context length. We observe that this works incredibly well for general videos because consecutive frames rarely provide any new information. Usually it's just moving very slightly from the previous frame. So that is semantic content that we can discard as an input to the video. Can you click this? Yeah. Thanks. So if we take a look, we are doing the same thing as before, but now we use the built-in optimization that we have in the Python SDK, and that gives us an optimized videos that's fitting comfortably within the 32,000 token limit. And if we use this to generate an embedding, you'll see that it should return a successful result. So in the previous case, we've now reduced the 720 frames of video, can someone help play this, please, into now just 88 frames. So we're dropping like 90% of the video content. But you can see that semantically, the video is still very similar. So even with this kind of aggressive downsampling, we're observing almost no loss in semantic content. And anecdotally, we have observed that this kind of dropping works very well in the general case. If you want more choice on how exactly to control the length of the context length, what we can do is called semantic video segmentation. So assume you have some data such as transcripts or captions associated with video. What you can actually do is segment your input video according to the timestamps and the captions, and this will generate more focused embeddings, which are especially good if you have longer videos with more diverse content, etc. So yeah, to wrap up, Voyage Multimodal 3.5 is an industry-leading multimodal embedding model that unlocks use cases like text-to-video retrieval, video-to-video retrieval, and multimodal RAG. And we give you the flexibility for any kind of deployment pattern with a lot of dimensionality and quantization options. letting you build whatever video retrieval system you might dream of. There's a Voyage Multimodal 3.5 blog post that was published today. If you want access to that, find me after the session, and I can give you the link. And if you want to learn more about the Voyage AI platform and how we're actually serving these embeddings, I highly recommend you check out the Inside the Voyage AI platform session, which is happening here, I believe, at 12:30. Next.